The mathematical formula for the normal distribution is a bit daunting. The mathematical formula for the normal distribution is f of x equals 1 divided by sigma times the square root of 2 pi. E, that's the natural logarithm e, raised to the negative x minus mu squared divided by 2 sigma squared. E is the natural logarithm, which is equal to approximately 2.71828, and pi, of course, is our old friend from geometry class, 3.14159. Mu is the population mean, and sigma is the standard deviation of the population. Before we get too anxious, we will never have to do math in this formula, I promise. Yes, the area under the curve is probability, but we have a very neat way to avoid integral calculus to get our answers. The normal distribution has many very helpful properties. It is symmetrical, so the mean, median, and mode are all the same value. 1/2 of the probability is on the left side of the mean, and 1/2 is on the right side of the mean. Further, the distribution is bell-shaped so that the probability of events further and further from the mean are less and less likely, exponentially less likely. The normal distribution has two parameters that control the location and shape of the distribution, the mean and the standard deviation. There are an infinite number of standard deviations and an infinite number of means. Thus, there are an infinite number of possible normal distributions. Here we see 3 distributions that all have the same mean, but different standard deviations. Because the area under the curve for each distribution must remain at 1, the curve must change its shape to accommodate different standard deviations. A distribution with a large standard deviation will be wide and flat, like the one marked with a standard deviation of 20. Perhaps this would be the distribution of ages for a whole city. The distribution with small standard deviation will be tall and narrow, like the one marked with a standard deviation of 5. This might be the distribution for ages of people living in nursing homes, where the ages are more like each other than across the whole city. We can see intuitively that if we go out 1 standard deviation on a distribution with a small standard deviation, it will capture more probability than on a distribution with a large standard deviation. The reason is the standard deviation is a measure of sameness or differentness, as we discussed earlier. A distribution with a small standard deviation is one where the observations are relatively homogeneous. One standard deviation captures many of them. The opposite is true for distributions with large standard deviations.